Okay, so, yeah, sorry, I mean, my handwriting is bad. If you can't read anything, please let me know, okay? Because yeah. So, what I've written here just is, again, the Hamiltonian for the model that we're considering, the clean electron gas, but now changing to a momentum orientation. So, where now the non-interacting part just has become diagonal. Yeah, so we have translation invariance, so this is just given by kinetic energy, and then we have creation and annihilation operators now in K representation. The interaction term is now given by the Fourier transform of the potential, which is E squared over Q squared, and reminding charge neutrality. And then we have here the fourth term. The interaction term now is expressed in terms of three momenta. This is because, I mean, we have a momentum conservation. Okay, so momentum conservation fixes one of the momentum, all momentum has to be conserved, so we have three momentum, and sigma prime are again spin up and spin down. Okay, so as a check, or probably you have done this several times, but if not, it's good to once do the exercise to go from the real to the momentum implementation. So there's still one, oh, I did write it down, there should be some factor, normalization factor 1 over 2 we had, and then out to the d, I guess, which comes from the Fourier transform. Okay. So this is the problem that we want to address, but first let's look at the non-interacting. Just to recall some things about the non-interacting electron gas. So, just a brief reminder that one interacting case we have electrons are described by the Fermi distribution function. F like Fermi distribution function. Which tells you about the occupation of a given state with energy epsilon k, and in the zero temperature limit, this actually just becomes the theta function. Also, all states are occupied which have energy smaller than epsilon k smaller than mu, then this is negative, and this the limit to 0 just gives a 0. So it's 1, and for energies above chemical potential, this is positive. So this gives theta minus epsilon k. And this is what you learn in statistics for any non-interacting Fermi gas. So what you have here is the distribution, and here is the energy epsilon k. So at zero temperature, you will have just the occupation being 1 up to the chemical potential mu, and then it drops to 0. And at finite temperature, this will broaden here, and this broadening is of the order of temperature. Okay? So this is like will be the starting point, and typically what we are interested in these cases is situations where the temperature is much smaller than the chemical potential. Okay, so the temperature is much smaller than the chemical potential. Well, you can think of all states being filled up here, and then you have here a small region where you have a softening of like a step function, and then nothing is occupied here again. So if you're in this regime, well, you can think that all the states filled up at very low energies, much smaller than the chemical potential, well, they are kind of inert. They don't have any energy to excite the state from up here to up here. Okay, so they just don't have the energy in the system. So all relevant physics actually will be playing around energies of the order of temperature around the chemical potential. Yeah? So we already know from this, well, there should be an efficient description which only takes into account, let's say, the physics going on in the temperature regime around the Fermi energy of the chemical potential, and all this here shouldn't be too relevant. Okay? But first let's recall, so that's a picture that the ground state of the non-interacting problem H0, so the ground state of this Hamiltonian here is just that all energy eigenstates given by k squared over 2m, they are filled up uniformly occupied up to the chemical potential. Okay, and I mean that's of course how the chemical potential also fixes the number of particles in the system. But just there. Okay, so we can think of this. Let's make a cartoon in 2 dimensions. So 3 dimensions is harder to draw, but 2 dimensions. We have, let's say, ky and the kx. The energy, constant energy, corresponds to some given circle. So this would be, let's say, the circle with radius given by the Fermi momentum, which is 2m chemical potential. Okay, and this is what we just said here. Well, the ground state is that where you fill up all states, all k states. Like if you take the boundary conditions or whatever, you have just say quantized value for your momentum, and what you do is you just fill up all momentum states, and because you have spin degeneracy, you can fill up every state with a spin up and spin down, and you fill up all the states in the sphere, which I try to just draw here. Okay, so this would correspond to the ground state of the non-interacting system. We just fill up everything up to the Fermi momentum, so we can define the ground state as there's some normalization factor, and then what you do is you take the product of all creation operators which have spin up and spin down, and energy smaller than the chemical potential, and you act on the vacuum state, which is here, state with no electrons. And this is some normalization factor. Okay, so that's the ground state of the non-interacting electron gas. And knowing that, you can then already calculate the ground state energy and density. Just for reference, later reference, let's note this. So the ground state energy is calculated by summing up the energy. So it's only the kinetic part. I mean, you don't have any interaction. So just summing up all the energies smaller than the chemical potential. So there's a factor 2, which is from spin. The spin degeneracy gives a total factor 2, and then we sum up over all momenta with modulus smaller than 2m mu. And what we sum is k squared over 2m. And if you do this, you get the following: you get L to the cube, 10 over pi squared, kf to the pi over m. Okay, so that's just a simple calculation. Probably everyone has done this in statistical physics once. This is the ground state energy, and we have the density. In the same way, it can be calculated by summing up. So we divide by L cubed because we calculate the density, not the particle number. the 2 is again due to spin degeneracy, and what we sum again is all states with momentum smaller than the Fermi momentum, and what we sum is just the 1, so we count how many states we have with momentum smaller than the Fermi momentum. If you do this, you'll get k Fermi to the cube, v squared, and from this we already see that k Fermi here. So this is all for 3-dimensional systems. Scale this n to the 1/3. And we can express actually, if you want, you can express the ground state energy also in terms of the particle number. So this would be 3/5 times total particle number. There should be some mu, I guess. Yeah. Okay, so this is just basic things one can calculate for the non-interacting problem, and then one can still think about excitation. So this is the ground state of the non-interacting problem, and then one can think about excitations. So if we again, let's say, make a picture for the 2-dimensional system, we said that the ground state just corresponds to the filled Fermi sphere filled all states with momentum smaller than the Fermi momentum. Then excitations can be just adding extra electrons, or just destroying some electrons or making some hole. So this would be just some excitations above this ground state. Okay? And now what we want to do is we want to address the interacting system, and we want to see how this changes. Okay? So the first thing is that we will look at the weakly interacting regime and just try to identify again what are the ground state energy, what are the relevant excitations. And after that, we will come to 2 examples where we see that there is an instability of this interacting. So if you start off from the non-interacting system and you introduce some interaction, there can be an instability where, the ground state will be different from this, where interactions change the ground state. But the first thing we'll just consider is the weakly interacting electron gas, and to get an idea of what weak interactions mean, we have to make some simple physical arguments to see what actually is the relevant physical parameter that allows us to talk about weak interactions. Okay? So the general idea first is that, well, the non-interacting problem is readily understood. So what happens if we introduce now interactions into the system? So the basic idea is always that we say, well, if the interactions is very weak, we hope that nothing drastic will change. So there's some adiabicity in the problem that we can slightly turn on interactions, and the only thing that will change is, well, the ground state will still look something like that, and there's still excitations, which now will be, let's say, the electrons and holes, which are just dressed by interactions with other electrons and holes, but there should be some adiabatic continuity that we can one-to-one follow how an excitation of the interacting system evolves from the non-interacting system by just slowly switching on interaction. So this is all the idea behind Landau liquid theory, and all the Landau liquid phenomenology, that we say, well, we hope there's some adiabatic continuity. Slightly small, switch on interactions. If it's very small, nothing drastic will happen. Only these, let's say, excitations will be addressed. Now, what we will see in the superconducting case, for example, that this is not always guaranteed. So if you have a very small, positive interaction, which in this case will be mediated in superconducting case, like in the standard PCS theory, by the phonons, and this completely breaks down because your ground state will change due to the presence of arbitrary weak interactions. Okay, it doesn't always have to hold, but it's some very successful. See all this idea of Landau liquid theory where you say, well, if interactions are very, very weak, there should be some adiabatic continuity. So now let's take this line of thought for the moment and then see what it actually means to have weak or strong interacting. So let's now turn to the interacting electron gas. Again, the electrons just interacting by Coulomb interaction, moving again on positive background. We make some qualitative, consider some qualitative aspects. So our hope or our assumption is what I said, so when interactions are weak, in what sense we have to understand better. We expect, or one might expect, that properties of the non-interacting system do not change dramatically. For example, the excitations are still in some sense electrons and holes, but stressed by interactions, so the interactions will be then say, of the quasi-particles, which are electrons and holes stressed by interactions. Stressed by interaction. This is the underlying idea of a liquid or Landau liquid theory. Okay. So again, the idea is, well, there's a one-to-one correspondence between the excitations of the non-interacting and the interacting problem. The only thing that should probably happen is that we get some renormalization of let's say the physical parameters of the non-interacting system, like the mass can be changed, renormalized due to interactions, and so on. Okay? So, but then, I mean, here's a statement about weak interactions. So we have to ask under what physical conditions are actually interactions weak. Okay, so we just say, well, interactions are weak if, I mean, so in the non-interacting problem we just have one energy scale, no? We just have the kinetic energy of the non-interacting electrons. Now once we turn on interactions, we have two energy scales. We have the kinetic energy and we have the interaction energy. So then it's just natural to say, well, interactions are weak if the energy due to interactions is much smaller than that due to the kinetic energy. So, well, there should be interactions are just a weak perturbation to the non-interacting problem. If the ground state, let's say, energy of the interacting problem of the interactions is much smaller than the kinetic part. And this then allows us to get some estimate or some idea of the physical parameter that will decide whether we are in the strongly interacting regime where this would be of the same one or larger than this, or the weakly interacting regime where this actually holds. Okay? So the physical parameter controlling now the interaction strength, and this means the relative interaction strength, or the relative strength of interactions compared to the kinetic, can be found from estimating just the two contributions, from estimating the two contributions that contribute to the ground state energy, which is kinetic contribution to the ground state energy and the interaction part. Okay, so let's use this picture to try to identify the parameter that decides if we have weak or strong interactions. And this is all very qualitative, just, to get some feeling or some idea of what might be going on. And of course, later on, when we do the calculation, we should try to see, to verify if this picture holds, if this is a good picture or not. So let's just make some very simple estimate, and this is, well, if we want to compare these two contributions, let's just assume that each electron in the metal occupies on average some volume given by some radius. Each electron occupies on average some volume fixed by some radius r0. Okay, so three-dimensional. So let's think of the entire system consisting of like these spheres, which are like the typical space occupied on average by an electron. Okay, so you have interactions, they don't want to come too close to each other. On the other hand, you don't want to localize the electrons because this will cost you a lot of kinetic energy. So let's make the picture and say, well, there's some radius r0 which arises due to the competition of interactions, and the kinetic energy which will be the, like, fixing the volume each electron has on average. Okay? So if you have the simple picture, then we know that the kinetic energy is just given by the radius of the sphere, okay? So the typical energy, kinetic energy of the electron is just given like, as more as you want to localize a particle, the larger will be the kinetic energy. It's just like the kinetic energy of a particle in a box, okay? So we see that the kinetic energy becomes larger and larger the smaller the radius will be, okay? On the other hand, the interaction, well, it's just given by E squared over R0, okay? So now we can, just from this simple estimate, compare the two contributions. So this is just given by E squared over R0 divided by H R squared 2M over R0 squared. So we get R0 squared up here, so all this is proportional to R0, and then all of the rest here, this is a dimensional quantity, so all of the rest has also to combine into some length scale. So let's call the length scale A0, and if you look at this length scale, this is H bar squared divided by 2M E squared. And this is known as the Bohr radius. Okay, let's forget about the factors 2 or whatever. And somehow we're just making some very qualitative estimates. Okay? So this means that actually from this very simple estimate we get an idea of what is the quantity which controls if interactions are small or large. So if the typical like volume or radius of the sphere an electron occupies is smaller than A0, then this will be small, meaning that interactions will be smaller than kinetic energy. We are in a small or weakly interacting regime. Whereas if this is a large number, well, then this is very much large. This is also large, and this means that we are in the non-perturbative or a strong interacting regime. Now, this is, tells us that if R0 is small, interactions are small. Now, if R0 is small, this means that we are considering actually many electrons. So where R0 is small, so we are considering the dense limit. So at large electron densities, we see that in the limit of large densities, the interactions are weak. Okay? And this is just resulting from the fact that the kinetic energy and the interaction energy both increase as the density increases, but the kinetic energy increases with 1 over radius squared, while the kinetic energy was 1 over radius. Okay? So we first found a dimensionless parameter, and again, this is only very quantitative arguments, and we have to confront them later with our calculations. Dimensionless parameter. Which is controlling the interaction strength or the relative relevance of the interactions compared to the kinetic energy. So this is also called RS, which is radius of spherical volume. Spherical volume containing on average 1 electron, and this radius is measured in natural units, which is the only combination you can arrive at that, like to get some length scales from the parameters of the problem. You have some h squared or e squared. Okay. But so as said, R0 is nothing but given through the density. So meaning that actually the physical parameter is controlling the relative strength of interactions. It's the density. So the density is the relevant parameter controlling the relative strength of the electron-electron interactions. Electron-electron interactions, meaning that we can, in this simple argument, distinguish two regimes. So there's the high density electron gas, where this ratio is much smaller than 1, equivalent to saying that the interaction energy is much smaller than the kinetic energy in the high density limit, which corresponds to the weakly interacting regime. And then there's the opposite limit of low density electron gas. So this just means low density electron gas where RS is much larger than 1, meaning that the interaction energy is much larger than the kinetic energy, meaning that we are in the Pauli interacting regime. Okay? So that's fine. Just, I mean, again, just very qualitative considerations, but we should see that actually this parameter RS will be popping up in the microscopic calculation. Now, having identified this, one should ask, well, what about like the real metals that we can think of? What is the typical estimate for this parameter RS there? And then one finds that most metals lie actually in a regime of what's called intermediate coupling, where you're not in either of two cases. Where typical values of RS is say between 2 and 6, intermediate coupling. Now we can ask, okay, so if we are now considering the weakly interacting electron gas, why should it apply? And well, it turns out that the calculations that we do still match very well most of or many metals. And the reason is that something one also often encounters in physics, that actually we are often quite lucky. I mean, it doesn't always hold, but often one finds that the regime where actually everything is well defined and well controlled, where one can do the calculation, often does not really match with the regime of parameters which apply to the physical situation. But often this idea of adiabicity, like also already said, like in the Landau liquid regime, that nothing much drastically should happen if one extends this regime a little bit, actually applies. So often one still finds that the theories that are well defined or are developed in certain parameter regimes actually also are a good description of systems which are actually outside of the regime of referenceability. So that's something one often encounters. So however, there's overwhelming evidence which suggests that weak coupling description, so the idea that interactions are weak, that one is in the weakly interacting regime, description holds even outside the regime of parameters over which the microscopic theory can be actually justified. Microscopic theory can be justified and principle behind this is the idea of adiabatic continuity. Which also, I mean, the underlying idea of the Landau liquid theory. Which is a phenomenological theory which will well describe these intermediate regimes in many cases. Okay. Questions or let's see. Questions?
consegui entender pela informação que o senhor colocou ali. Altas densidades, você vai ter uma interação fraca. Não deve ser o contrário, não?
Pois é, isso é muitas assim, vezes fica confundindo essa coisa, mas é o seguinte, você tem duas energias, tá? Você tem a energia cinética e a energia dividida pelas interações. E você tem que comparar as duas. Agora a ideia é muito simples, se a gente faz essa divisão falando que, ó, se a gente tem um sistema interagente, o elétron, eles não gostam de ficar muito perto um do outro, mas eles vão simplesmente ocupar um espaço que é restrito pelo fato que os elétrons não gostam de ficar muito perto um de outro. Então, se você tem essa ideia que você tem essas esferas que, on average, na média, o elétron fica. Agora você tem que perguntar como essas duas escalas de energia dependem disso. Então você tem a energia cinética, que você sabe que uma partícula preso numa caixa, ela tem uma energia cinética que escala com o inverso desse radio. Se você faz a caixa menor e menor e menor, a energia cinética está crescendo, 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 porque a partícula não quer ficar localizada. E ela está crescendo com o momento quadrático. E o momento é só escalando com 1 sobre o tamanho da caixa. Então, isso em conta, você vê que isso, na verdade, está crescendo quadraticamente com o inverso de R0. Tá? Bom, vamos esquecer esses dois. A energia cinética está crescendo com 1 sobre A0 quadrático. Isso simplesmente vem do fato que a energia cinética típica é com 1 sobre A0, mas, bom, a energia cinética é P quadrado, tá? É 1 sobre A0, tá? Então, o maior a densidade, o menor é A0, e o maior se cresce. Agora, a segunda contribuição é simplesmente a interaction, que simplesmente, bom, você tem Coulomb interaction e essa partícula tem um Coulomb interaction que é simplesmente 1 sobre A0, tá? Agora você vê de novo, essa interação vai ser a menor A0 for, mas só linearmente com o inverso. Então você agora encontra a situação, bom, o maior a densidade, o menor vai ser o espaço ocupado, né? Vamos chamar isso de R0 tilde. E R0 tilde é muito menor do que R0, e N tilde muito maior do que N. Tá? O maior a densidade, o menos espaço eles têm. Tá? Então, os dois casos você vê que esse espaço que um elétron tem vai diminuir o maior for a densidade, mas a observação é muito simples, que você tem que comparar essas duas escalas. Tá, você tem razão. O que você fala, mas o maior a densidade não deveria ser que maior a densidade foi, o maior vai ser a interaction energy. Você tem razão, é descrito aqui. A energia, por causa das interações, vai crescendo com a densidade, o maior for. Mas o que você não está tomando em conta é que não faz sentido falar só quanto é a interaction energy, você tem que falar da razão das duas. Você tem que falar quanto é a interaction energy comparado à kinetic energy. E aí você tem que tomar em conta, mas a kinetic energy também vai crescer. O maior for a densidade, o menor foi o volume que o elétron ocupa. E a observação é que essa está crescendo quadraticamente. E agora, se você comparar os dois, você vê, a razão, em vez disso, você tem razão, isso é proporcional ao inverso de A0, mas essa razão, se eu divido e se eu faço disso uma quantidade dimensionless, essa, em vez de ser proporcional a 1 sobre A0, ela é proporcional a 0. A única coisa que você fez, você falou, essa é grande, mas comparado a quê? E tem que comparar com isso. E aí você vê, aí acontece essa coisa que você pensa dessa forma, está tudo certinho, mas você tem que comparar essas duas escalas de energias. E aí você vê, não, aí acontece exatamente, o maior foi R0, o menor foi R0, meaning o maior foi a density, o menor relativamente à energia cinética vai ser energia. Tá? Então isso a gente sempre pensa dessa forma, mas você tem que pensar dessa forma. Tá, bom. Então, vamos deixar para